Hi, I'm sorry I can't be with you in person, but COVID finally struck. So the work I want to present today is a collaboration from many people, and some of them are shown here. Earthquakes have killed nearly 1 million people since the year 2000. This is an example from the L'Aquila earthquake in Italy that killed around 300 people. Here's a photograph from Haiti where more than 100,000 people lost their lives. Volcanic activity has resulted in hundreds of thousands of people being evacuated from their homes, and it shut down transatlantic travel in 2010, as many of us will remember. Close to home, the UK is impacted by ground movements such as sinkholes and landslips. The take-home messages from this talk are that we can now measure ground movements from space with extraordinary precision with InSAR. Mass processing of Sentinel-1 InSAR in particular is a game changer for monitoring our hazardous planet. And to stop hazards becoming disasters, we need transnational and transdisciplinary collaborations and partnerships. So what is InSAR? Well, here's an interferogram. You can see these coloured interference fringes, and these are formed by differencing two SAR images that are required, in this case, before and after a big earthquake that struck Nepal in 2015. It not only affected the region around the epicenter near Gorkha, but also impacted Kathmandu more than 100 kilometers away. So how do we form these images, and what do they mean? I like to use this rather simple cartoon, which is not to scale. Here's Sentinel-1 flying at 600 kilometers above the Earth, emitting a wave with a wavelength of around 6 centimeters. Sentinel-1 comes back on a different date. If the ground has moved, then the path length has changed. And even though we don't know the precise distance from the satellite to the ground, we can measure that very small difference very precisely. And we can map that out. And each of these you can think of as a contour of the amount of ground movement with a contour interval of around 3 centimeters. We can also count those interference fringes, color in the image, so we can look and see which parts of the ground have moved towards the satellite, in this case caused by uplift, or have moved away from the satellite. And we can take that data and then use it to work out how much movement occurred on faults, for example, by using geophysical modeling. So this is a 3D view of the Nepal, the fault underneath Nepal, which shows the amount of slip that occurred on that fault in the earthquake. You can see there was around 6 meters of slip at the peak, if not more. Probably equally important is this area of low slip, which we think in the shallow part of the fault didn't fail. We think that's locked and could fail in a future earthquake. And really, one of the really valuable things from Sentinel-1 is we can do this kind of analysis very, very quickly now, within a few days of most earthquakes. So Sentinel-1 is a game changer. It's an operational radar. Like all radars, it's all-weather, day-night imaging, but it's able to acquire data over very, very large areas. In fact, over the entire planet, either twice every 6 or 12 days when 2 satellites are operating. It's designed for InSAR, so it actually has a really boring long-term acquisition strategy, acquiring the same data type again and again and again. So you can build these long time series. And it's funded for at least 20 years, with 1A launched in 2014, 1B operating from 2016 to December 2021. 1C has just been announced that will be launched in early 2023. And importantly, it has a free and open data policy, which means we can mass process data over very, very large regions in a way that was just impossible with previous satellites. And that's whether you're a commercial organization or an academic organization. I want to show one example of that from work we've been doing in Turkey. This is an ambition we have, which is not just to measure the earthquakes, but also to measure how the plates bend in the periods building up to earthquakes. And that bending, if we can map that, we can say something about where earthquakes will take place and how often they might take place. In this case, we're looking at one single frame of Sentinel-1, but we can repeat that analysis. Each analysis involves many hundreds of images, and we can repeat that over the whole country. And for these ascending passes, we're actually seeing the westward motion of Anatolia as motion towards the satellite. In descending passes, as the satellite's going from north to south and looking west, the westward motion is motion away from the satellite, and that gives us these red colors. And you can see the change in colors across folds. We can convert that into something that's easier to interpret, in this case the east-west velocity field at the top and the vertical velocity field at the bottom. The east-west is dominated by the tectonics. You can see these big changes in color associated with the major faults. The vertical velocity field is more associated with things like water extraction and mining. We can turn that velocity field into a strain measurement, so that's a measurement of the amount of that tectonic bending, and that's really useful for trying to forecast seismic hazard. And you can see this is a seismic hazard map for Turkey, and you can see the correlation between the two data sets. And within the COMET group in Leeds, we're mass processing data from Sentinel-1 over the entire Alpine Himalayan belt with the aim of improving estimates of seismic hazard, particularly in areas where they don't have many instruments on the ground. You can get all that data as well from our online interactive portal. I now want to switch to the Galapagos and think about volcanoes briefly. So here's an example from some work we did in 2017 in response to a request from colleagues in Ecuador who were in charge of monitoring this volcano. What we saw in the interferogram was that we had subsidence near the peak of the volcano and uplift off to the south. And what that meant was magma was moving sideways in the subsurface. And this was part of the evidence that local scientists used to lower the alert level. And we're now automatically processing data from all the volcanoes around the world. And again, you can go on our interactive portal and produce your own graphs that look like this. This is from Sierra Negra, also in the Galapagos, which has experienced over 2 meters of uplift since late 2016. You can also see these drops in the time series, for example, in summer 2018, associated typically with eruptions at the volcano. And so this is a very powerful data set for volcano monitoring. Close to home, the University of Leeds spin-out SatSense, which you'll hear more about later in this meeting, is using InSAR to monitor hazardous ground movement across the entire UK, keeping a live deformation data set for the UK. If we zoom in on Ripon, if we zoom in on the centre, you can see a little red blob there. If we keep zooming in, we can actually look at a time series of those points and see how those individual points are moving through time. And in this particular case, you saw about 1 centimetre of subsidence that preceded that sinkhole that I showed you in the beginning of the talk. I want to end the talk by really thinking on a bigger picture of what we're trying to achieve here. So in Haiti, something like 100,000, maybe as many as 300,000 people lost their lives. But actually we knew, so the scientific community knew about the risk there. We knew that there could be a big earthquake. And so I like the slogan of the No Natural Disasters Organization, that while some hazards are natural and unavoidable, the resulting disasters are almost always have been made by human actions and decisions. And you might have heard the phrase, earthquakes don't kill people, buildings do. And I think that's true, but I think there's a bigger question, who allowed those buildings to be built? Why was resilience to seismic shaking not a priority for decision makers? And so something we're working on extensively is working on collaborations between physical scientists, social scientists and practitioners, working with decision makers to try and understand how we can use scientific information and the latest innovations in techniques like InSAR and other tools to actually have a direct impact on reducing the risk from eruptions, volcanoes and other natural hazards. Earth observation data and SAR is a key technology for that, and in particular the Sentinel-1 Copernicus missions, but also the ongoing plans for the L-band SAR that we hope will be launched before 2030, and the Sentinel-1 next generation missions. All of these are key for global Earth observation because they're the only systems really that have the capacity to make observations globally all the time. The commercial satellites are fantastic for targeted studies, but they can't acquire these global data sets. And so it's really important that we continue to support that as a nation. So I want to end there again with my take-home messages. And I hope I can talk to some of you either via video calls during this meeting, or please feel free to contact me and set up a separate meeting. Thank you.